Hello, welcome back to my channel. This is Jane. Today's language is MATLAB. Today I'm going to talk about how to solve ordinary differential equation, aka ODE, and teach you about that. Okay, in MATLAB there are a lot of methods to solve ODEs. However, I will show you the easiest methods for it. Therefore, I've excluded the methods using ODE 23, ODE 45, and so on, so that you should watch other videos. So if you want to know about the methods using ODE 23 and etc. Okay. Okay, let's get started. First method is the one using dsolve function. For this method, as you can see, you should declare yt and t about sims like this. Sims y t t. So here clear. So okay, and yt means y is a function of t. To define ordinary differential equation, you will need some derivative functions of yt, right? So for this you can use the function of diff. So dy is equal so the function of diff has some parameters which are a function and domain of the function and differentiating order. At this time, the differentiating order has 1 for a default value. So here y t and d2y is diff y t 2 like this. So okay, and then the dsolve function can automatically solve the ODE which are given to the dsolve function for the parameter. To define the ODE, you can utilize the predefined derivatives of the function yt, this dy and this d2y. So equation is equal to d2y plus 4 times dy plus 3 times y, and here should be equal. It is not equal, so equal. So and then this is 0. So it means y prime plus 4y prime plus 3y is equal to. So we so if you use dsolve function, then dsolve function will find the function of y from this differential equation. Okay, so the solution will be y, so and then dsolve function and here eqn like this. So okay, so you can tell like this, and you can solve the ODE like this. Okay, and then execute. Oh, I'm sorry. So here execute. So this is the solution of this differential equation. Oh, this is really simple, right? And the next method is applying initial conditions. Okay, the basic form is the same with the previous method, and this method is the case that there is one initial condition. Okay, and then eqn will be like this. Okay, 3, and then here it's equal to power t to power okay, 2 and times y. Okay, and then initial conditions will be if y0 is equal to 1, then you can add the initial condition like the similar way with EQ equation. So like this, cond is a variable for the initial condition. So cond is and y0 is equal 1. Okay, so and y-sol is equal to dsolve EQ and conditions are cond. This is an initial cond. So and then domain is t. So like this, cool. And then execute them. Then like this, you solved this ODE. Cool. And the next method is the case that there are two initial conditions. For the simplest example, we can think of the harmonic oscillator of a spring. So you can define an ODE like this. Okay. EQN is d to y plus b is damping coefficient and k is spring constant and is equal if external force is sine t, then like this, and then m mass is 1 and damping constant is 3 and spring constant is 10. Okay, cool. And then let's suppose that an initial position is 1 and an initial velocity is 0. So dy0 is equal 0. So like this, you should bind these conditions to apply the initial conditions to the zero function. So the variable cond will save the bind initial conditions. So cond, and you can bind the initial conditions using this bracket. So like this, cond 1, cond 2. Okay, and then y solve t and dsolve EQN and like and parameter cond execute. Then like this. Oops. You can find like this, and this is a solution, and if you substituting each one into each positions, then you will get the real solutions. So, okay, so like this you can find solution. Okay, cool. And then the last method is using Laplace transform. So for this, you should define the variables using sims. Define t and s and capital Y, and then the constants are like this. Okay, so and then if initial conditions are like this, and then external force is sine t, right here. At this time, you don't have to define small y. and the initial conditions are like this, and then let the function of f be an external force. So f will be sine t, so that the capital F will be a Laplace transformed function of a small f. So Laplace transform and small f and t to s. T to s. Laplace transform function means Laplace transforming the function f of domain t into domain s. Thus, if first order term of ODE is transformed, then y1 is like this. Y1 is like this as y minus count 1. Also, the y2 written like this recursively. Times y1 minus count 2. So this is y prime Laplace transformed y prime, and this Laplace transformed y2 prime. Okay, and then you should rearrange these equations about y, right? So solve m times y2, capital Y2 plus b times capital Y1 plus k capital Y minus times y minus capital F, and about y. This is y blah 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 blah. If you inverse Laplace transform this solve, then you can find the solution function. So like this, inverse Laplace solve like this, and from S into T, and then execute. Oh, I'm sorry. So this is not like, it should be like this. I'm sorry. And then okay, then execute. Then you can find like this. For now, this is a plus section. If you want to see the graph of the solution function, you can use two functions. One is easy plot and the other one is f plot. The easy plot is not recommended, however you can use it also. You can see the graph if you use easy plot y so, and this is domain 0 to 10 and 0 to 5, and then you can use also f plot y so and 0 to 5, and then execute. You can see the result like this, right? So this is same result like this. Then here like this. Two graphs are same, like this, right? So like this, you can see the graph like this. And okay, good. Thank you for watching this video. And if you visit my GitHub site below, you can see my MATLAB file as .mlx and learn about decorating the graph and other useful functions for ODE. Okay, thank you everybody. See you next video.